Imagine someone hands you a phone book with 1 billion entries, no order, no index, nothing alphabetized, just 1 billion random names stacked in 1 billion random rows. Now imagine they ask you to find one specific name hidden somewhere inside it. Your only option is to check entries one at a time. On average, you'd have to look through 500 million of them before you got lucky. That is not a made-up scenario to sound dramatic. That is, mathematically, exactly how hard it is for a classical computer to search through unsorted data. And for decades, computer scientists simply accepted it as an unavoidable law of computing. Then, in 1996, a researcher named Love Grover found a way to search that same billion-entry phone book using roughly 31,000 steps instead of 500 million. Not by cheating, not by sorting the data first. By using the actual physics of quantum mechanics to search in a fundamentally different way than any classical computer ever could. This is Grover's algorithm, and understanding how it actually works is one of the clearest windows anyone has into what a quantum computer really is and why it can do something a classical computer, no matter how fast or how large, can never do it all. Before we get to the algorithm itself, we need to get one very common misconception about quantum computers out of the way immediately, because almost every popular explanation of quantum computing gets this part wrong. The common story goes something like this. A quantum computer uses qubits, which can be both 0 and 1 at the same time, so it can check every possible answer simultaneously, and that's why it's fast. That explanation isn't just oversimplified, it's actually misleading in a way that hides the real magic. If a quantum computer really could check 1 billion possible answers all at once and just read off the correct one, it would search that billion-entry phone book instantly in a single step. But Grover's algorithm doesn't work in a single step. It takes roughly the square root of the number of entries, about 31,000 steps for 1 billion entries, not one step. That gap between instant and 31,000 steps is not a rounding error. It's the entire story of what a quantum computer can and cannot do, and it's exactly where Grover's algorithm becomes genuinely beautiful. This misconception persists because it's the version of quantum computing that gets repeated the most often, in headlines, in casual conversation, even in some well-meaning textbooks that oversimplify for the sake of a quick explanation. And it's an understandable mistake, because superposition really does let a quantum computer represent every possible answer at the same time, which sounds exactly like it should let you check them all at once for free. The problem is what happens the instant you try to look. Measuring a quantum system doesn't let you peek at all the possibilities and pick the best one. It forces the entire system to collapse down to just one single outcome, chosen essentially at random according to the probabilities baked into the system at that moment. If every possible answer currently has an equal probability, measuring gives you a uniformly random guess, no better than picking a random row in that billion-entry phone book yourself. So superposition by itself buys you absolutely nothing. The entire challenge of designing a quantum algorithm is figuring out how to manipulate that superposition before you ever measure it, so that the probability of measuring the correct answer becomes large, while the probability of measuring anything else becomes small. Grover's algorithm is the answer to exactly that challenge for the specific problem of unstructured search, and understanding how it pulls that off is what actually explains quantum computing, rather than gesturing vaguely at parallelism that doesn't really exist the way people imagine. So let's actually build this up properly. Starting from the ordinary bit, you already understand. A classical bit is either a 0 or a 1 full stop at every single moment in time. A qubit, the quantum equivalent, does not simply sit at 0 or 1. It exists in what's called a superposition, a combination of both states at once, and crucially, that combination isn't just a 50-50 coin flip waiting to be revealed. It's described by something called an amplitude, a number that determines the qubit's relationship to being measured as a 0 or a 1. Here's the part almost nobody explains clearly enough. Amplitudes can be negative. A regular probability can never be negative. You can't have a negative 20% chance of something happening, but a quantum amplitude absolutely can be negative, and that single fact, that amplitudes can point in different directions and even cancel each other out, is the entire engine behind every advantage a quantum computer has ever demonstrated. To make that concrete, imagine 2 waves on water approaching each other. If both waves are rising at the same point, they combine into a taller wave, what physicists call constructive interference. But if one wave is rising while the other is falling, they can partially or even completely cancel each other out, destructive interference. Quantum amplitudes behave exactly like this. When you combine or manipulate qubits, their amplitudes can interfere with each other the same way those waves do, reinforcing certain outcomes and canceling out others. A classical bit has nothing remotely like this available to it. It's simply on or off, with no wave-like quality to exploit, no possibility of 2 classical states partially canceling each other into a smaller likelihood. This interference behavior, borrowed directly from the wave mechanics that govern how quantum particles actually behave in nature, is the single ingredient that separates everything a quantum computer can do from everything a classical computer can do. And Grover's algorithm is one of the clearest possible demonstrations of harnessing it deliberately and precisely. Now picture this. Instead of one qubit, imagine we have enough qubits to represent every single entry in our billion-row phone book as a distinct possible state. Using 30 qubits, since 2 to the 30th power is a little over a billion, we can put the entire system into an equal superposition across all billion possible answers simultaneously. Each one of those billion possible answers now has the exact same tiny amplitude, and if you measured the system right now, you'd just get a random entry, no better than guessing blindly. This is the critical point everyone misses. Superposition alone gives you nothing. Simply spreading your system across every possible answer does not help you find the right one, because measurement just collapses everything back down to one random result with no better odds than picking blindly in the first place. The genuine trick, the actual algorithm, is what you do to that superposition before you measure it. This is where Grover's algorithm actually begins, and it works using 2 repeated steps, applied over and over in a specific rhythm, like swinging a pendulum with careful, precise pushes. The first step is called the oracle, and think of it as a black box that can recognize the correct answer without telling you what it is directly. When the oracle looks at the superposition of all billion possibilities, it does something subtle and strange. It flips the sign of the amplitude belonging to the correct answer, and only the correct answer, turning its amplitude from positive to negative, while leaving every other amplitude completely untouched. Nothing about the probabilities has changed yet. Remember, probability comes from squaring the amplitude, and squaring a negative number gives you the same positive result as squaring a positive number. So if you measured the system immediately after this step, you'd still get a random answer, with the correct one no more likely to show up than before. The oracle didn't make the right answer more probable. It just marked it secretly by flipping its sign. The second step is where that secret marking actually gets converted into something useful, and it's called the diffusion operator, sometimes described as inversion about the mean. Here's the geometric picture that makes this click. Imagine every single amplitude in your system, all billion of them, plotted as heights on a graph. Before the oracle, they're all sitting at the exact same height, forming a perfectly flat line. After the oracle flips the marked answers sign, that one entry now dips slightly below the line, while everything else stays exactly where it was, essentially unchanged, since it's just one flipped value among a billion. Now calculate the average height of that entire graph. Because only one entry flipped negative out of a billion, the average barely moves at all. The diffusion operator then reflects every single amplitude across that average, as if that average line were a mirror. Watch what happens to the marked entry specifically. It was sitting below the average by some small amount, so reflecting it across the average doesn't just bring it back up to where it started, it flips it to the same distance above the average instead. Meanwhile, every other entry, which was already sitting almost exactly at the average, barely moves when reflected, because they were already close to the mirror line to begin with. The net result of one oracle step, followed by one diffusion step, is that the marked answer's amplitude grows slightly larger, while every other answer's amplitude shrinks slightly. Do this once, and the effect is small. Do this again, oracle then diffusion, and each repetition nudges the marked answer's amplitude a little higher, while the rest keep shrinking. It behaves almost exactly like slowly rotating a needle on a dial, tilting it degree by degree away from pointing at a random guess and toward pointing directly at the correct answer. And this is precisely why the number of steps needed scales with the square root of the total number of possibilities, rather than the total number itself. Each repetition of the oracle and diffusion pair rotates your system's overall state by roughly the same small angle, and you need approximately the square root of n repetitions to complete that rotation and land the needle pointing squarely at the right answer, ready to be revealed the moment you finally measure. There's a subtlety worth pausing on here because it's exactly the kind of detail that separates a genuinely correct understanding of Grover's algorithm from a hand-wavy one. If you keep applying the oracle and diffusion steps past the optimal point, roughly the square root of n repetitions, the needle doesn't just stay pointed at the correct answer. It keeps rotating, swinging past the target and back down toward a random guess again, then eventually back up toward the correct answer, oscillating the whole way, the way a pendulum would if you kept pushing it well past the top of its swing. This means Grover's algorithm has a very specific number of steps that gives you the best possible odds of measuring the correct answer, and stopping too early or running too long both hurt your chances. That precision is part of what makes it a genuine algorithm with a provable, calculable stopping point, rather than a vague process you just run until it feels done. This is the answer to why quantum computers are fast for this specific kind of problem, and it has almost nothing to do with checking every possibility simultaneously the way the popular explanation claims. It has everything to do with amplitudes that can go negative, canceling and reinforcing each other through careful, repeated manipulation, gradually steering the system's state toward the correct answer through what is essentially a geometric rotation happening in an abstract space with a billion dimensions. Classical computers have no equivalent operation. A classical bit cannot have a negative probability to exploit, cannot be rotated through superposition, and so a classical computer really is stuck checking entries one at a time, with no way to build up constructive interference toward the right answer the way Grover's algorithm does. It's worth being precise here about exactly how much of a speed up this actually represents, because it's genuinely impressive without needing any exaggeration. Searching a list of n unsorted entries classically takes, on average, n over 2 steps, and in the worst case, all n steps. Grover's algorithm needs approximately the square root of n steps. For our billion entry example, that's the difference between roughly 500 million steps and about 31,000 steps. A speed up of more than 15,000 times. That's an enormous, genuinely transformative improvement. But notice something important. This is what's called a quadratic speed up, not an exponential one. Square rooting a billion gives you 31,000, dramatically smaller, but not so small that the problem becomes trivial or instant. Compare that to a completely different quantum algorithm, Shor's algorithm, designed for factoring large numbers, which achieves an exponential speed up, turning problems that would take classical computers longer than the age of the universe into problems solvable in hours. Grover's algorithm is not that kind of speed up. It's a real, provable, mathematically guaranteed advantage, but a more modest one, and that distinction matters enormously for understanding what quantum computers will and won't be good for. And here's a detail that makes Grover's algorithm even more remarkable rather than less. In 1996, the same year Grover published this result, other researchers proved something called the BBHT bound, showing mathematically that no quantum algorithm could ever search an unsorted list faster than the square root of n, no matter how clever the approach. Grover hadn't just found a fast algorithm, he'd found the fastest algorithm that could possibly exist for this problem, full stop, an optimal result with a rigorous mathematical proof standing behind it. That's an unusually clean and satisfying kind of result in computer science, where you don't just get a good answer, you get proof that a better one is mathematically impossible. So where does this actually matter outside of a physics classroom? The most immediate and consequential impact of Grover's algorithm shows up in cryptography, specifically in symmetric encryption, the kind of encryption used to protect huge amounts of the internet's day-to-day traffic. Things like AES, the advanced encryption standard that secures everything from your banking app to encrypted messaging. Breaking a symmetric encryption key by brute force means checking every possible key value until you find the one that works, exactly the unstructured search problem Grover's algorithm was built for. A sufficiently powerful quantum computer running Grover's algorithm against a 128-bit AES key wouldn't need to check all two to the 128th possible keys. It would need roughly the square root of that number, which mathematically works out to the equivalent security strength of a 64-bit key, weak enough to be a genuine concern. This is precisely why security agencies and standards bodies around the world have been pushing organizations to move toward AES 256 rather than AES 128 for anything that needs to remain secure for decades to come, because Grover's algorithm effectively halves the security strength of symmetric encryption in bits, and doubling the key length in advance is the straightforward fix. It's important to be clear here about scale and timeline, because this is exactly the kind of claim that tends to get wildly overstated. Running Grover's algorithm against a real encryption key isn't something that happens on a whiteboard. It requires a fault-tolerant quantum computer with enough stable, error-corrected logical qubits to hold the key's search space. In superposition and run potentially billions of oracle and diffusion steps in sequence without the fragile quantum state collapsing along the way. Today's quantum computers, even the most advanced ones from Google, IBM, and other leading labs, are nowhere near that scale yet. And serious estimates for when quantum hardware could meaningfully threaten strong symmetric encryption through Grover's algorithm generally point toward many years out, not next year and not next month. The threat is real enough that cryptographers take it seriously today, but it is a threat on the horizon being prepared for in advance, not an emergency happening right now. Beyond cryptography, Grover's algorithm and its underlying technique, amplitude amplification, show up as a building block inside a surprisingly wide range of other quantum algorithms. Anytime a problem can be framed as searching through a large space of possibilities for one that satisfies some condition, whether that's finding the minimum value in an unsorted dataset, solving certain optimization problems, or searching through combinatorial puzzles, some version of Grover's core idea, flip the sign of what you're looking for, then reflect everything around the average, tends to appear somewhere inside the solution. It has become one of the fundamental tools in the quantum algorithm toolkit. referenced constantly in quantum computing research precisely because the trick it demonstrates, using negative amplitudes to build constructive interference toward a correct answer, generalizes to so many other problems beyond simple search. Researchers have also found ways to adapt the core idea for more specialized situations. There are variants that search for the minimum or maximum value across an unsorted collection rather than a single marked item. Variants that handle the case where more than one entry in the database satisfies the search condition, and variants tuned to work more efficiently when you have some prior information about how likely different answers are to be correct, rather than starting from a perfectly flat, equal superposition. Each of these builds directly on the same oracle and diffusion rhythm at the heart of the original algorithm, just adjusted slightly for the shape of the specific problem being solved. That flexibility is part of why Grover's algorithm has remained relevant for nearly 3 decades since its original publication. Far longer than most individual pieces of computer science, research tend to stay at the center of an active field. It's also worth understanding why this particular algorithm has become such a common teaching tool for explaining quantum computing to newcomers beyond just its elegance. Many other quantum algorithms, including Shor's factoring algorithm, require a fair amount of background in number theory or abstract algebra before the mechanics really make sense. Grover's algorithm doesn't. Its underlying explanation reduces to geometry you can literally sketch on a napkin, a needle rotating slowly toward a target with each careful push. That accessibility, combined with the fact that it demonstrates true, provable quantum advantage rather than a purely theoretical curiosity, makes it one of the very first real algorithms taught in almost every serious introduction to quantum computing, whether in a university course or in research papers written for physicists just entering the field from a classical computing background. What makes Grover's algorithm such a genuinely great entry point into understanding quantum computing as a whole is that it strips away almost every layer of unnecessary complexity and shows you the actual mechanism at work, with nothing hidden behind jargon. You don't need superposition alone, and you don't need entanglement in the way people often assume, to get a real quantum advantage here. What you need is negative amplitude, repeated careful rotation through superposition, and the patient, structured accumulation of probability toward a correct answer, step by step, exactly the square root of n times, no faster, and provably no faster than that is even mathematically possible. It's not magic. It's not instant. It's a genuinely elegant piece of mathematics turned into an equally elegant piece of physics. And once you actually see the mirror and reflection geometry underneath it, you understand something true and specific about quantum computing instead of the vague, slightly wrong version most people carry around in their heads. If this finally made quantum computing click for you, that's exactly the kind of understanding worth sharing. So pass this along to someone still stuck on the wrong version of the story.